matrices and systems of equations, how do I expect you to fill these in without even having learned anything? Priyanka.
It would be like the stuff around the
Yeah, like what? Substitution, that was 7.1. Elimination, that was 7.2. Row, echelon form.
And then the
7.3. Okay, I think it's a little weird. It's partial fractions, that was 7.4. Good job. But I don't think we actually solved systems of partials. Inequalities came next. Gaussian elimination, that's kind of technically in this one.
Yeah, it's part of the rational.
Linear system.
We could do graphing. Yeah. Just in general, graphing is the other way. Would you guys kind of use your calculators? Didn't you kind of use them throughout chapter 7 here and there
for checking stuff.
ln's and e's and checking? Yeah. Or like intersections with parabolas and circles sometimes if they were gross. So graphing's kind of in and amongst all of these. But what's the title of this section? Is it just systems like we've already done?
Matrices.
Ooh, matrices. Nice thing is, matrices, wait a minute, when's this homework? Oh, I didn't put it up. Yes, I did. When's this homework due?
Thursday.
So this must be a lot more than just like a basic intro. Because wasn't 7.1 like a 1 there? Okay, so this might not just be review, but let's see. Matrices. I need you guys to find the matrix button in your calculator. Notice how do we find matrices? X negative 1? Is that the reciprocal button or the inverse button?
Wait, what?
Inverse.
Did they all say just more?
Bye, Marco.
Come back. Ooh, calculus. You guys aren't there yet. Okay, hold on. I do see matrix. I do see a second x to the negative 1. But how do you guys know whether this is a reciprocal button or an inverse button? What could you try to do?
Press equal.
Chris, what is it?
Enter.
It's a reciprocal button. Oh, that's the reciprocal button. Okay, so second reciprocal, because it does 1 over 2, right? The reciprocal button goes to matrix. Wait a minute. Doesn't e to the being above ln and 10 to the being above log and square root being above x squared, don't some of these buttons have a particular relationship to what they're above? Right? What is the relationship of e to the ln or 10 to the log or square root of squared? They're inverses. I wonder if this button is going to inverse. I wonder if this button, not really, I don't know, nothing important. I wonder if this button has anything to do with matrix. Maybe yes, maybe no. Okay, so what if I just hit that? That wasn't very exciting. Okay, hold on. Second, inverse, no, reciprocal button. Ooh, there's a whole menu of stuff. Okay, but what else? Why am I having you come here? Because we are about to write a little bit of notes about the entries and the order of a matrix. The order, I'm going to call them M by N, like a 2x4. If you go to Home Depot, like, I want a 2x4. Do they know what you're talking about?
Yes.
Yes, because it's probably a piece of wood, and it's of a certain size, 2 indicating the width and 4 indicating the length, right? A 2x4. So if I say, hey, I want an M by N matrix, do you know what I mean? Do you know what I mean? And more specifically, if I'm talking about a specific place in the matrix, do you know what I mean?
Yes.
First of all, I want you guys to make me a 2x4 matrix. Just to keep in with the wood example. A 2x4 matrix. Make me a 2x4. Yep. Make me a 2x4. And what do we notice about the size? 2x4. Yeah, but 2 is what? The width and the length. I can't really use that in matrices, but I can use rows
And groups.
and columns. Right? What holds up a building?
Foundation.
Okay, good call. What holds up a patio cover?
Little
Rows or columns?
I don't have a back door.
Columns. Think like Greek architecture, the big old columns in like the Colosseum. Colosseum? I don't know. Colosseum doesn't really have columns. But out like in the front. The thing in front. I forget what it was.
I like everything that's Greek is Rome.
Okay. Shh. Columns. Do we have columns? Yes, they're the up and down ones. Do we have rows? Yes, they're the side by side ones. Who is who? 2 indicates the number of
Rome.
and 4 indicates. Let's get that in our notes, please. There was a question I totally breezed over. I am apologizing now, but I am available now. What was the question?
Oh, how did you get in the calculator? How did you get to that point where it was?
Help them out. We went second,
And then you go to edit.
Reciprocal
press
button.
A.
Yeah, no.
and then go over to edit.
And then hit A.
Because we're making.
Oh, I see.
Yeah. So we have a 2 by 4, 2 rows, 4 columns. And I want you to put, just fill it in with 1, 2, 3, 4, 5, 6, 7, 8. The way I said that, try hitting enter. How does it naturally go? Across. Good. So 1, 2, 3, 4. You just hit enter, 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 enter. And then 5, 6, 7, 8. My question is the following for the next one. So you hit 1, 2, 3, 4, 5. My question is the following. Which number is in the A2? Oh, that's no fun. The A12 spot.
2.
There is no 12. It's only 2 and 4. There are only 8 things total. I'm not talking about 12. What am I talking about? Rows and columns. So which row?
1.
Rows come first, columns come second. Rows come first, columns come second. Row 1, which column? That's confusing. Why aren't there commas? I don't know. Look at your calculator. They do commas there. The notation is there, just written weird and written different. Check it. Don't you have a... go away. Bye-bye. Don't you have A12? But instead of showing it in like function notation, like A, it's term A of first row, second column, we just write it as a little baby subscript. A12. Yeah, you guys were right. 2 is in A12. So my question next is, what A would 7 be in?
2, 3.
2, 3. Anybody ever played Battleship when they were younger?
Yes, I love that.
Oh, I'm not saying whether you love or hate it, just saying.
It takes too long.
Just lazy.
Rotation.
Okay, I'm talking about like locating things, that's all. Shh, focus. So, 7 is in the second row, third column across, yeah? So when we go to label this in our notes, we say, a quick reminder of, oh, wait a minute, didn't we already say that row was the end guy? And column was the end guy?
Something like that, the numbers about the way it breaks, so it's like 214.
You have to think context of the size of matrix that you have.
What if it's like 20 rows or 14?
In context of the size that you have. Yeah. We don't normally have that many, but if we did, and we'd probably start doing a calculator notation every time. The book doesn't go the book doesn't go that much.
Okay.
I don't think you'll see anything beyond the 10 by 10. That's good for that page. What's it going? Smart words, all kinds of funky today. Here we go. So, what's the order of the first one?
1, 1.
The order of the feet? I mean, no, just 1, 1. That's it. 1 row, 1 column. You're welcome. I'm not a true nerd, but I can pretend because I have lots of things.
1 by 3.
1 by
4.
4. Just because that's a 0 doesn't mean there isn't still a place for it. Does that make sense?
Yeah.
How about this one?
2 by 2.
2 by 2. How about this one?
3 by 2.
3 by 2. 3 by 2. Now, can I show you something tricky?
Yes.
It's not that tricky, but do you realize this could be a 1x minus a 3y plus a 0z is 1/2? Pretend the smart board is working. Because it'd be 1x minus 3y plus 0z is equal to 1/2. Question, can we solve very much if we just have this? No. How many of these would we need? Two more, because wouldn't we need 3 equations with 3 unknowns to try to get like a unique solution? Interessante. Anyway, just quick little foreshadowing of what's to come. Okay, but are we okay with orders and at least knowing the order or being able to interpret the order? Yeah. Worst comes to worst, and if you get totally confused and you're allowed to use your calculator, can't you go to edit your matrix and remind yourself of which one is which by creating a 2x3 or a 3x4?
Sure.
Snazzy. It's like cheating, but it's just using your resources. Here are a few other just getting used to matrices terms that we should talk about. Now you guys notice a few things. You notice I'm talking about like A11, A21, A31. I'm reminding you of that little notation. Or A11, A12, A13, reminding you of that notation. A row matrix only has a row, a column matrix only has a column. A square matrix has the exact same number of rows and columns. And there was only one square matrix on the page before, right? Wasn't it that 2x2? 2 rows, 2 columns? But it could have been a 3x3, a 4x4, a 5x5, a 10x10, a 100x100. Matrices. There's a whole section of college math called linear algebra. Linear algebra is basically a class learning more and more about matrices and matrices applied. And guess what major has to have linear algebra apart from math majors, applied or pure? What's the one other major that always has to have linear algebra? It has in the last like 5 years. The last 5 years, besides math, besides applied or pure math.
Engineering. Chemistry.
Probably engineering. But engineering has to have like all the math, so this is kind of a but yeah, probably engineering. What's the specific part or category? Other major that's much more precise, much more specific that engineers use. That's not their main skills. C.
Computer science.
Yes. Programming. Computer science for programming. You have to take linear algebra. Linear algebra is fully dependent on matrices. Now, engineers definitely have to know something about programming or something about computers, right? And linear algebra isn't just for programming, that's just one application, but yeah. Muy interesante. We have rows, we have columns, we have square matrices, we have identity matrices. Identity matrices.
Binary code.
Ooh, 1s and 0s. Nice.
Matrix.
But in this one, the identity matrix is a very specific placement of 1s and 0s. Where are the 1s?
They're aligned.
1x, ooh, 1y, ooh, 1z, ooh, 1a. I don't know
Beta.
something else. Beta, sure.
On the row matrix, is it A1M?
Ooh, yes, because what did we have being our number of rows a second ago? See it? M was how many rows, N was how many columns. So I'm just saying you could go up to 10, 100, 1,000, a million, 10, 100, 1,000, a million. But remember, M is the number of. Ooh, wait a minute, hold on. Which one was M? So we should switch them, huh? This one should be N, and that one should be M. Why? Because M was how many rows, and doesn't how many rows determine which one goes here? Good catch, guys. And how many columns determines which one goes here? Oh, and it's not way too big. You're struggling so hard. Okay. Yeah, that makes sense, because how many columns will be the N, and how many rows will be the m, which is awkward though, because m is the number of rows and it's in the column matrix, and n is the number of columns and it's in the row matrix. But why is it called column matrix? Because it's a column, only one. A row, one row, only one. But this next one doesn't matter because it could be MM or it could be NN. It just means they're the same thing. So however many columns is however many rows, NN, or however many rows is as many columns, so MM. That's the same thing either way. And that last one, the identity matrix, once again, it's a main diagonal. That's a snazzy way of saying it. A main diagonal of ones. Everything else zeros. It's not always possible to get the identity matrix, even if we want to. That's a big part of this introduction to matrices that we're going to try a lot. That we're going to try to get the identity matrix a lot. Why would we try? Well, it's really helpful to know the identity of a solution. You think of it that way. So it's some size square matrix with a main diagonal of ones and zeros elsewhere. If anything else shows up, it's not the identity. It might be as reduced as possible. Sometimes you can't go all the way to the identity, but it's not the identity unless you have a main diagonal of ones and everybody else is zeros. Okay, vocab. Vocab, terms. We gotta get beyond terms. We're getting closer and closer and closer to actual problems when we start talking about augmented matrices. Augmented matrices are basically like, hey, they're coming from a system of equations. That's at least one way of looking at it. They're coming from a system of equations, and so they will have this variable matrix over here, which has like all your x coefficients, y coefficients, z coefficients. I need this to be square for a lot of different reasons. We'll talk about it later, but we have a square matrix, so we need to have a square matrix of the variables, but then we're also augmenting it with the solutions. Oh, augmenting it with. I feel like I've heard that word before. You guys should look up that vocab. It's not just math. But an augmented matrix, taking the variable coefficients and taking the constants and putting them together. We have a square matrix over here. We have a column matrix over here. We're putting them together, and yet we're treating them in some ways distinctly, and yet in some ways treating them all together. Or forming them, bringing them all together. The cool thing is, oh my goodness, row echelon Gaussian elimination is back. It's just going to look a little different as to how we do it. In my mental mathers, it's going to be fun. My non-mental mathers, you're going to want to get a whiteboard. My mental mathers is going to be fun. My non-mental mathers, you're going to want to get a whiteboard. Or do your homework on this page and have your scratch paper be this page. You could do it that way too. Have your homework be this page and your scratch paper be this page. And then you turn it over, scratch paper, work, and just like have homework every other page. That could work too without a whiteboard. Because we're going to take these systems and we're just going to be playing with the numbers and not having to basically be showing quite as much work as we did before. Because we were working in section 7.3 with 3 equations, 3 unknowns. What if we have 4 and 4, or 5 and 5, or 6 and 6? We don't want to have to keep on writing all that work that we did before. It'll be much simpler, much easier, and much more possible to program if we get them into matrices instead. Instead of like actually writing all the x's and y's and z's or a's and b's and s's. Yeah, that was the motion. Free falling. So this is where it gets interesting, and this is why homework isn't due until Thursday. How do we do the same work as section 7.3? How do we do the same work like section 7.3, but with matrices? Once again, what we did in 7.3 is great and all, but I don't think I'd want to do that system for anything more than a 3 by 3, in the sense of 3 unknowns, 3 equations. But of course it goes actually 1, 2, 3, 4 columns because we also have our solutions. REF, row echelon form. Might be good to put over here just a quick little row echelon form is RE. Okay, guys. Okay, I need to orient this or else I'm going to die. And what this does not say is it does not say reduced row echelon form. It just says row echelon. In row echelon form, you guys remember we needed the stair step, right? Now, reduced row echelon form gets us all the way to the identity. Row echelon form, what we're trying to get is basically main diagonal of ones, zeros underneath, but then we can have whatever else we want in the rest of the matrix. Row echelon form. We're going to try to get our ones, we're going to try to get our zeros underneath, but we're not going to really stress too much if we're just doing row echelon form with getting zeros above. Okay? Now the nice thing is we're humans, so if we look at this system and if we just take all of the coefficients and if we just put them into the different spaces in the matrix, having our x's, our y's, our z's nice and organized, our constants at the end, we're allowed to put whatever equation we want on top. And I want this one on top more than any of the other ones just because it has a leading coefficient of, which is exactly what I want for my identity matrix. The problem is, I'm trying to show you the system without really writing out the words yet. Once we get the one, some people would be like, yeah, let's get another one. Yeah, let's get another one. The problem is if we go get ones without establishing our zeros in this column first, we're going to throw the whole thing off as soon as we go over here. So we start column by column. We work column by column. And we get our 1 first, and then we tackle our zeros. Then we move on to the next column, getting our 1 where we want it to go, and then tackling our zeros, and then we move on to the last column. We get our 1. We have our row echelon form. All we have to do is back substitute because, think about it, we would have a 1z equals a 1y, plug in the z equals a 1x, plug in the x and y, sorry, the y and z equals. It'd be ready for back substitution. So I want you guys to think elimination, just like 7.3. I want you to think elimination, just like 7.3, except this time we're not calling these by 1 and 2 and 3, equation 1, equation 2, equation 3. We're calling it by row 1, row 2, row 3. And row 1, row 2, row 3 are going to keep changing and changing and changing as I do my matrix math. So row 1 is referring to what is in row 1 in the step before. Not what was at the very beginning, but what was in the step before. Now, I'm going to go ahead and leave my row 1 exactly as it is because I like that 1 exactly where he is. What I don't like is row 2 and row 3 because they need zeros and they don't have them. But if I do row 1 plus row 2, what's going to happen? Yeah, and I'm going to get 0, which is exactly what I want. But I'm going to keep on adding the rest of them. So row 1 plus row 2, awesome. But how about row 1 plus row 2 for the second column? How are we doing? How do I get all these new numbers to put in my new row 2?
You just subtract it.
And to be super specific, technically we shouldn't just write what we did, but we should also write where it's going to be super specific. It's like a little baby equation, just kind of showing our work. Well, remember the book's going to actually write paragraphs. We're just going to be like, row 1 plus row 2 going into row 2. So 1 plus negative 1, negative 4 plus 3, 3 minus 1, 5 minus 3. See how I'm saying my mental math there? So you're like, oh, no big deal, I can add. Right? Here's the problem. How am I going to get rid of row 3? Now, some of you are like, hey, times 2 plus. I get it, but we're not going to always have these numbers that we necessarily want right here, but we are always going to have a 1 before we go tackling these two, because we get a 1 in the first step. So instead of using this one, I'm actually going to use negative 2r1 plus r3.
I still don't understand why we can't use the second.
We can, as humans, but if we're trying to think towards technology and programming, etc., we want to think about what we can do every time. And if there's always a 1 in this column, in this spot, I can always multiply him by the opposite of whatever that is. In a program, it could be like, hey, whatever you have there, cool, just him times negative that and add, and it'll always work. What will always work? I'll always get 0. Because negative 2 times 1 plus 2. Now, carefully, you're going to have a little bit more mental math capacity, right? Because now I have to do negative 2 times who? Which is positive 8 plus 0. See it? Finish off the row. Negative 2 times the entry in the third column plus the entry in the third row. Negative 2 times the entry in the first plus the third row. So negative 6 minus 4 is negative 10, and negative 10 plus 6 is negative 4. My non-mental mathers. If that's like, oh, I don't know what's going on, what could you do? What you could do right here is you could actually take that little baby equation, do it off to the side. Oops. And you can just go through it and be like, oh, hey, it's negative 2, it's positive 8, it's negative 6, and it's negative 10. Every year I have at least a handful of kids that do it this way. And they, to be honest, rock it. And if they get their system down, they're more commonly right than the ones that do it mental math style. It takes them longer, but they're more accurate because they're going step by step. And come back in. Okay, do I have my first column? Wait, what do I need now? My second column. I need to get a 1. How am I going to get a 1? I'm going to multiply the entire row 2 by a negative. What's that going to get me? That's going to get me 0 times a negative stays 0, which is good. I need it to be 0. Times a negative, times a negative, times a negative. I'm going to keep these guys the same because that wasn't my job this round. My job was just to get the 1 in the new column. But as soon as I have the 1 in the new column, it's called establishing the 1. We can go tackle the rest of the column and get the zeros in the next step. And the cool thing is, if you're thinking programming, all I have to do once I know the 1 is just multiply this entire row by the opposite of whatever that entry is. So positive 4 times row 2 plus row 1 into row 1. For this bottom one, it'll be negative 8 row 2 plus row 3 into row 3. What's going to stay the same as we do this math is this one, because I'm not touching it. But also, negative 4 times 0 plus 1 is 0 plus 1. That stays the same. And 4 times 0 plus 0, I'm not messing up as long as I go column by column. I will keep whatever work I've done as I move forward. Now, if I do 4 times 1 plus 4, that'll be 0, just what I need. But I also need to do 4 times all the other entries. Negative 8 plus 3, negative 5. Negative 8 plus 5 will be negative 3. I have to go down here. Negative 8 times 1 plus 8 is 0. Perfect, I'm so close. I also have to do 16 minus 10 is 6, and I have to do 16 minus 4 is 12. But now my second column is done. So what am I going to go tackling next? My third column. What do I need? A 1. How do I get it? Divide by 6. Oh, I did a reduced row echelon form. I was supposed to keep them the same. That's okay. What am I going to get at the end? Did I do it right? 1x with the answer, 1y with an answer, 1z with an answer. If I tell a computer how to do that, it's called RREF in your matrix menu. You can take any matrix of any size and solve for all of your variables in one fell swoop. Bye, guys. Don't worry, homework's not due till Thursday.